was, so just let's do a tiny second of review from last time. The point was we were looking at the Lebesgue set of a function, right? So these are the points where if you look at f of y minus f of x in absolute value integrated over a ball dy, x is fixed, 1 over the measure of the ball, where the lim of this is 0, lim sup of this, lim and lim sup, over, as usual, can you see this? It's getting really tight.
The scans came out a little bit.
The scans came out better? That's a lim. That's a 1 over the measure of the ball. No, let me try this one. Maybe it's a little smaller tip. Where this limit is 0. Is that any better? Or is that about the same thickness?
It's the set of x.
The set of x, exactly. The set of x. So this is an integral in, this is the set of x.
Wait, is the integral of dy?
The integral is dy. The integral is dy. It's the set of x for which this thing is 0. And the question, so Robert's question was, why didn't we just, so the way we proved this was we replaced f of x by r, basically, for rational numbers that are nearby. And his question was, why not just set g of, well, I guess I can call it g sub x of y for a given x to be this absolute value, and then apply the theorem that we know. And what the theorem that we know will tell us that for x, for mu almost every x, the point is that the function is moving. I want to say something about mu almost every x, but the function is moving with x. And we don't have any uniformity in the proof of the previous version of the Lebesgue differentiation theorem. So the way to get around this is to replace the actual value of f of x by a rational value, prove it for any rational value, but of course the value of that is close to your favorite rational value. Okay, so I just wanted to make that quick little, it's not really review, but just a remark.
Should we maybe write down this doesn't work somewhere so we don't get confused?
Right, doesn't work, no uniformity in x. Well, there kind of is uniformity in x, but you have to prove it, and this is how you prove it, by replacing f of x by a fixed number, applying it at that fixed number. Okay, I just wanted to make that comment. Question? No? Okay, I thought I handed this up. All right, on to new things. The new things that we're covering are the Radon-Nikodym theorem and its consequences. So on to sign measures. It's a new topic. And vitally important topic. Signed measures. So definition, new. So if I have a measurable space, measurable space. So what's a measurable space? A measure space is you have a space, you have a sigma algebra, and a measure on that sigma algebra. Measurable is you have a space in a sigma algebra, you're just missing the measure. Okay? So measurable space, x mu, given that, nu is a signed measure. If nu is a function from measurable sets to possibly minus infinity, possibly plus infinity, so it's not just a positive function. I want it to be, I want nu of the empty set to be 0, and I want it to be sigma additive, so countably additive. Now there are a couple of caveats here because now we have positive and negative values, and so we have series that may converge but not absolutely. So for signed measures, this means something slightly more restrictive. First of all, nu can only take one of these values. Nu equals infinity implies nu does not equal minus infinity.
Anywhere? Like it can only take one of those for any
It can only take one of those values over all of mu, over the entire set of values. It either takes positive infinite values for some sets, but never negative infinite values, or vice versa, or it never takes positive or negative infinite values. Okay? But I don't want to be in a position where I'm taking infinity minus infinity. That has no definition. 0 times infinity I have no problem with. That's 0. Okay? A set of measure 0 times the value infinity, no problem, that's 0. The function being equal to 0 times the indicator of a set of infinite measure, no problem, that's 0. But infinity minus infinity, we have a problem. Okay, so only takes one of these values, so only takes at most one of plus minus infinity. And then countably additive, so if I have some disjoint sets En equals E, any set that I write from now on is measurable. We're not dealing with unmeasurable sets. So I'm not going to say 1,000 times where the ENs are measurable and their disjoint union is a measurable set E. Okay? So all sets that appear are measurable. Then nu of E should be the sum of nu of the ENs. And if nu of E isn't divergent, if nu of E is not infinity, that's an infinity, is not infinity, then I need this to converge absolutely. Converges absolutely. So if all of these things are satisfied, then I call nu a signed measure.
That's a disjoint union?
Disjoint union. Disjoint. If I had a thinner pen, I would write disjoint, but if I had a thinner pen, you wouldn't be able to read what I'm writing. Maybe I can do this.
You could do that thing where it's like a union with a cross in it.
Well, usually a square, big square cup means disjoint union,
Yeah.
as opposed to just a... That looks like a square. I mean, my handwriting is pretty bad, but this is quite distinguished from you. I don't know. Okay, any questions on what I mean by a signed measure? All right. Let's study signed measures, as they will be quite relevant in a lot of things we want to say. All right. Right, because now we have signed measures floating around, I'm going to be careful when I say usual measures. So usual measures in this context are positive measures. Okay? Sorry. Thank you. So by positive measure, I mean a measure that takes only positive values, which, if it satisfies all these conditions, of course, is a measure.
Isn't there anything regarding the monotonicity?
Well, the monotonicity, so for signed measures or for usual measures? For signed measures, no.
I mean, for like absolute values are less or something like that.
Well, we're going to get to that in a second. We're going to get to what the total variation is as a measure, and we'll see that. You'll see in a second. We're going to study the decomposition, but as a definition, no. Precisely because it can take positive and negative values, so there's no monotonicity anymore. All right. So just to give you an example of such, why would e.g. kind of a prototypical, not only prototypical but quintessential, actually. So both. For example, if you have what's a measure, if you have an integrable function that can take positive and negative values, you integrate it with respect to your favorite positive measure. That determines something that will be a signed measure.
And then what about the negative infinities and positive infinities?
Right, so
It's L1.
so if it's L1, then that's not an issue. Let's define extended L1 to exactly deal with this. Definition, F is in L1 extended. If, remember, F is in F plus minus F minus. F is a real valued function. It has positive values and negative values. And at least one of F plus minus is in L1. Okay? So if at least one of these is in L1, then this integral can't be plus infinity and minus infinity. So that's extended L1. This is called F is, let's say, extended mu measurable. Extended mu integrable. Okay? So it's not that it's integrable, but once it's not integrable, you're really in trouble because you don't know how to subtract minus infinity minus infinity. But only one of these is allowed to be infinity. Yes.
So I mean, 0 times infinity is usually indeterminate, and they were okay with making that 0. So why weren't they okay with saying infinity minus infinity is 0?
Because infinity minus infinity, what are you going to make it?
0.
But it might be infinity, or it might be negative
I'm
infinity.
just saying, while we're here, like, if we're breaking rules,
No.
why not just...
Well, right. Of course, it's up to you to define things however you want. The reason 0 times infinity is defined to be 0 is because there are two natural contexts in which that arises, already for simple functions. Right? You want to be able to integrate a simple function, so you could say it takes the value 0 on a set of infinite measure. Like the indicator function of the unit interval takes the value 0 on everything except the unit interval, which is a set of infinite measure.
Right.
I want to be able to integrate that and say that the integral of the unit interval is 1,
Okay, yeah.
and that'll be 0 times infinity.
There's no sense in infinity minus infinity.
We don't have to deal with infinity times infinity. Let's not. And it doesn't really make sense.
Right.
Because it very well, well, we want to have something that works reasonably. So that's why we make 0 times infinity be equal to 0, because it does what we want it to. That's the convention. If you're multiplying the value 0 times the measure of a set which has infinite measure, I want to be able to say that 0 times that set is the function 0.
Right. If you're dealing with an odd function, right, from 0 to infinity, it could be infinite, and then from negative infinity to 0, it could be negative infinity. But the integral would be 0.
The symmetric integral would be 0,
Yeah.
and we define integrals in you can define the Riemann integral, for example, on an infinite domain, could be anything that converges to that set. So depending on how if I take something symmetric about the origin, then yes, all of those integrals are 0 and the limit's 0. But if I skew them like this, and if I go twice this direction for 2x minus x to 2x, all of a sudden the integral is ruined. So there are no odd functions in L1 plus minus.
Okay.
That's in fact, I should, right, that's a good.
Well, sin x over x.
This is not a good example.
Is that odd? I don't know, but that kind of thing that just totally converted. Okay,
Right.
Something that's
There are no functions in L1 plus minus take away L1. That are odd.
Right.
Okay. So we don't want to be, unless you're making extra specifications about what you mean by the integral, but we want the integral to be some general thing, so we're not going to worry about infinity minus infinity. Look, again, this is something human beings decided to do because it works.
Wasn't it
So-
discovered?
So if you wanted to have extra conditions on what you do with infinity minus infinity, like integrate it symmetrically about the origin, where's the origin in an abstract measure space?
Oh, that's true, yeah.
Okay, so all kinds of things get very bad if you don't force at least one of these to be finite so that there's no... It's okay to have the total integral be minus infinity if f minus is not in L1, but make f plus in L1. Yes?
Is the EGs, it still works if you replace mu with the signed measure?
We haven't defined integration on a signed measure.
Okay.
We're about to.
Okay. Let's do that.
We will. We have to prove a couple of theorems before we can. But yeah, that's why I did it for a positive measure first, because we know what we mean by this integral. All right. Very good. Right, and what the Radon-Nikodym theorem is that this is the quintessential thing. So this is basically the only way to get signed measure as long as you're not absolutely as long as you're absolutely continuous. We're getting to these things. Anyway, this is like the prototypical, this is like the first one that you should see, and it's also all of the ones that you will see. Okay, let's do a proposition. So if you have sets EJ that are measurable, and they're nested, and their union is a set E, which is then measurable, then the measures of the EJs, I can't say increase, but I can say converge to the measure of E. And similarly, if EJs decrease to E and nu of E1 is finite, then nu of the EJs converges to nu of E.
This is the kind of thing where you can like drop some initial ones. Like you don't need E1 to necessarily.
It doesn't have to be E1 as long as one of them is finite. But you may as well just forget. So if they're zooming down, forget all the ones that have infinite measure, get to one that has finite measure. Okay, and the proofs are identical. So proof is the same. If you have sets that are increasing, if the EJs are, I guess it's kind of the same picture. You can't tell which order I drew these circles. But if they're increasing, then you break into, so if these are the EJs, you break into these shells. So Sj is EJ take away all the previous EKs. So that makes these disjoint shells, and E is the union of disjoint shells Sj. And so by additivity, countable additivity, and use countable additivity, and use disjoint Sj's plus countable additivity. That's the word additivity. Hopefully you can make sense of that. And if they're decreasing, then just do the same thing, but writing E1 as the disjoint union of these shells plus E, and then you can subtract E1 from both sides. It telescopes, you subtract E1 from both sides. Okay, that's the same. Now, if you have a signed, so definition, if U is a signed measure, then a measurable set E is called positive for nu if every measurable subset of E has non-negative nu measure.
What is this? Positive to
For nu. So if there's more than one sign measure floating around, then positive for what? Positive for this sign measure. Okay, so it's a set so that when you take any subset of it, including itself, so not only is the measure of the set positive, but any measurable subset has positive measure. That's what it means to be positive. Okay, and similarly negative, and similarly null. Okay. So a set is null if it and any subset of it takes nu measure 0. Now we want to prove a little lemma. Yeah, so in the case, let's just look at the example. So in the example that nu is an integral of an f, E is positive if f restricted to E is non-negative.
Is there like an almost everywhere thing you can do? Or?
We're about to prove a theorem well, I can just tell you what the theorem's going to say, but I need a little bit of preparatory lemata. The theorem's going to say that you can decompose a space X into a positive set and a negative set, disjoint sets, one of which is positive, one of which is negative. And the decomposition is almost everywhere unique. So unique up to changes of things of null sets. Okay? That's what we're working up to. And once we have that kind of a decomposition, then we have, that's called the Hahn Decomposition Theorem. Then we have the Disjoint Decomposition Theorem, which decomposes a measure into a plus part and a minus part. And then we can define integration by measures. Okay, so let's do the Hahn Decomposition Theorem. I need a little lemma. So we know what it means to be positive. We know that limits of sets survive limits of signed measures. So lemma, countable union of positive and also negative sets is positive. So this is very easy proof. So let En be positive and E be the union of the ENs. Let's turn this union into a disjoint union. Let Sn be En, take away anybody who came from a previous EJ. Then Sn is of course a subset of En, and E is a disjoint union of the Sns. Okay, so they didn't have to be nested anymore. We just are cutting it up into pieces. What are the new pieces that you need to add on at each stage to get all the way up to E? And so now let's take any subset of this set E. Let F be a subset of E, arbitrary measurable, always measurable. I'm not going to say that 1,000 times. What are we trying to prove? We're trying to prove, so we have this countable union of positive sets. I want to know that any subset of that positive union of positive sets has positive measure. What we want is that nu of F is non-negative. Well, what is nu of F? These sets are disjoint. F is contained in E. Nu of F is the sum of nus of F intersect Sn by countable additivity. All of these are subsets of Sn, which is a subset of En. These are subsets of En. The ENs are positive. Any subset of a positive set has non-negative, should really be called non-negative anyway, has non-negative measure. So you're adding up a bunch of non-negative things. And the same exact argument with just this last thing replaced by a less than or equal sign tells you that countable unions of negative sets are negative. So far, so good?
Also for null sets?
And also for null sets, yes. For again, exactly the same reason.
So is there, I thought about it and I changed. Okay, never mind.
What were you going to ask?
Can we do it for uncountable unions? And the answer is no, you could take just a single point that has like a negative value. And since it's a single point, it's a positive set.
Right.
But an uncountable union of it, you're in trouble.
Yep.
Okay, thank you.
Okay. So now let's state the Hahn Decomposition Theorem. I think I have everything I need. So again, countable unions of positive or negative sets are positive and negative. And let's state the Hahn Decomposition Theorem. Okay, if nu is a signed measure, there exist positive, negative subsets of X so that X is the disjoint union of positive and negative. Moreover, so that's part one, and part two, if P prime N prime is another decomposition, is another decomposition, then the symmetric difference between P and P prime, which is the same as the symmetric difference of N and N prime, are null sets for nu. Okay? Not only do they have measure 0, but any subset of them has measure 0. Nu measure 0. I guess nu sign measure 0. Okay. Let's prove a lemma to prepare for this. It's clear, right? It's clear what we're trying to say. You have kind of like, you're thinking of X as some big space, and I don't know what value nu takes on all of X. Maybe it only, maybe nu of all of X is finite, but it has positive infinity value somewhere, but it certainly then doesn't have negative infinity value somewhere else. But we sort of want to decompose X into like the plus part and the minus part.
What you said can't be true. If it has positive infinity value.
That's true.
Okay.
That's true. If it has positive infinity value somewhere, then it doesn't have negative infinity value anywhere else, and hence the union of those two will be all of X, which will have positive infinity value. That's right. If X has a finite value, then nu is finite everywhere. That's right. What I want to say is, so let's do it in the case that it doesn't take negative infinity. So assume nu does not equal negative infinity. Otherwise, replace nu by negative nu, and then what I'm saying is correct. Or replace nu by negative nu. Then, if I have a negative set, if I have a set, let's call it D, let's say a measurable set with negative measure, that doesn't mean the set itself is negative. There could be subsets of it that have positive measure, but then there exists a set A, let's say F subset of D, which is negative, and the nu measure of F is only more negative than D. So let's just think about this. Maybe D, I guess it's kind of here. So here's X. Maybe D, this is all of X, this is D. D overall is negative, but maybe I can throw away some positive part, throw it away, and that leaves me with a set which is this set that I'm trying to call F, which is even more negative, and not only is it a little negative, it's totally negative. Okay. Does that make sense? So I'm going to throw away anything that remotely resembles a positive set, positive measure subsets of D, and I'll be left with something that's totally negative, and that will not increase. How could it increase the nu measure of D? Okay, that's what we want to prove. So let's start with D0, which is just D itself, and let T0 be the supremum over all the measures of all subsets of D0. Okay, so I take all possible measurable subsets of D0, and I look at their nus, and I look at the largest one. It might be infinite. Could be infinite. Could be infinity. That's okay. Either way, so one thing I do know, since the empty set is a subset of D, you can't do worse than, can't be negative. 0 is one of the values of the supremum, so it can't be negative. Okay? So because I have this t0, now if the value of t0 is 0, then we're done. Question?
What are we assuming about the nu of d0?
Nu of d0 is nu of d, and nu of d is negative. So all I'm saying is I have a set that overall is negative. I want to throw out any positive bits of it and be left with a totally negative set. And when I do that, the measure will decrease. It's more negative than the original d. Okay? It might be that we're done already. If t0 is equal to 0, then d is already negative because the largest value of any subset of d isn't positive. So it doesn't have a positive subset. Okay. But let's, even if that is the case, we can continue with the proof. So whether t0 is positive or not, and whether it's infinite or not, doesn't actually matter. There does exist, so there exists some subset, let's call it E0 of D0, such that the new measure of E0 is at least, well, T0 over 2, say. So the case we're worried about is when T0 is positive. I do want this to be finite, though. So if T0 is giant, let's just say the smaller of T0 or 1. I do want this to have positive measures so that I can sort of add and subtract things. Okay? So I'll find an E0, which has mu at least T0 over 2, because T0 is the supremum, so anything approaching the supremum. This could be 0, in which case that's fine, just take the empty set. But, so this is this is getting towards the largest positive set that we have in D. Okay? This is a supremum, so there's not necessarily an E0 that has measure T0, but there's certainly something that gets close to T0, like T0 over 2. It's close enough for our purposes. Okay? So when we do that, we're going to remove this set from D. So let D1 be D0, take away this E0, this very positive set. It's so hard to draw large enough. Okay? And let T1 be the sup over all of the subsets of the measures over all the subsets of D1. Continue by induction. So dn will be dn minus 1 take away en minus 1. And then tn will be the largest thing, the largest that we haven't taken away yet. And then what do I want to take away? Can you see that? So what I want to take away, there exists some set En, subset of Dn, such that its new measure is at least Tn over 2, and well, if that's huge, then just chop it at 1. Just to keep it finite. Okay? So what are we doing? We're taking D0, we're taking away E0. So we have a subset where we've taken away the sort of the largest measure, or a set of good measure. Then we take away E1. By the way, E0 and E1 are disjoint because we took away E0 to get to D1, and now we're looking at subsets of D1. So the E note, ENs are disjoint. And now let's set, what did I want to call this thing? F. F is my totally negative set. Set F to be D take away the union of all of the disjoint union of all of the ENs.
How do we know that we can choose EN to measure exactly 1 if Tn is infinite?
Not exactly, just at least.
How do we know we can do that? How do we know there's a finite thing? What if like they're all infinite?
If they're all infinite,
Yeah.
if all of the ENs have positive infinite measure,
Yeah.
then this is perfectly fine because I'm just saying
Yeah.
make it at least measure 1.
Okay.
And infinity is bigger than 1.
A little bigger than
A little bigger.
Can you say again why we included the min of 1?
Yeah, I just don't want to say give me a set of infinite measure.
one. It's fine if you do.
It is fine if I do. Somehow I prefer to deal with finite things when what I'm gonna be doing in a second is adding and subtracting things, and I rather have inequalities where I'm subtracting not infinite things. Although we will only have infinity on one side or the other. Okay.
But we just said that we might not be able to guarantee that we get something finite for EN.
No, it's actually okay. You'll see in a second. We will never be subtracting infinite values. It's I don't know. It's a pedagogical. This one is not a serious thing. All I really want is that nu of En is at least Tn over 2. There's really no good reason to put that minimum on. I'm just trying to not force. You see, no. Sorry. There is something to say here. If the soup is infinity, but it could be that each of the sets has finite measure. The sets could have arbitrarily large finite measure, and if Tn is infinite, then Tn over 2 is still infinity, but there is no set which has measure infinity. So this is saving me in that case. Should I say that again?
Yes.
So let's say that Tn, the soup could be infinity, while all of the sets themselves have finite measure.
That's because signed measures fail to be.
No, that could be the case just in measures. You can have things of measure 1, 2, 3, 4, 5.
And then you would take their union.
Yes, although,
Which is
well,
still contained in Dn.
I guess their union is still contained in Dn. You could. I'm being less.
But that fails for signed measures because you don't have the monotonicity between those.
For example, you don't have the monotonicity, right? You could have things that have all. You can argue your way out of it by some other means. I think putting min 1 is the easiest way to argue your way out of it. So the point is the Tn could be infinity, but there isn't necessarily a set which does have infinite measure. And so let's guard against that by saying, well, just give me some large enough value if this thing is infinite. And if it's not, then just, sure, you have an infinite size set, throw it in. Or actually throw it out. Okay? So, this is a countable disjoint union, the ENs. And so nu of F is equal to nu of D minus the sum of nu of the ENs. That's by countable additivity of nu. The ENs are all disjoint, so alternatively, put this sum on the other side, if you want. All right. Now, all of these sets, so we know that this is negative. All of these sets are at least size 1, at least size 0. I mean, this min is non-negative. And so I'm adding a bunch of non-negative things. I'm actually subtracting a bunch of non-negative things. And so this is less than nu of D. And the only thing I have to prove for you is that nu of F, so there are two things that I wanted in the lemma. I wanted nu of F to be at most nu of D. That we have satisfied. F is indeed a subset of D. F is a subset of D. Nu of F is at most nu of D. I need to know that nu is negative. Okay? That F is negative. Okay? So let's see what would happen. So if F is not negative, if there exists some set I don't know, what should I call it? S in F with nu of S positive. If it's not negative, then there's some set that has positive, strictly positive value. Well, what does it mean that this nu of S has survived all of these cuts? Remember what the T's are. The T's are the supremum of the subsets of what was left over. That means that whatever the supremum is, it's bigger than nu of S. So what I'm trying to say is Tn is at least nu of S for all n.
Why do I know that I can, when I take nu of f, that I can subtract the set difference?
This is just the countable additivity. In other words, first of all, we have measurable things, and there's a call this E.
Yeah, but I remember in regular measures, that's not always true. Like you need the thing you're subtracting to have finite measures, like to actually subtract it.
To be measurable, right? So I know that nu of f. I know that nu of d has negative.
If you move the minus to the other side, I agree that it's true.
Right.
Is that sum finite?
So, well, I'm about to argue that if this sum is infinite,
Okay.
remember what the first thing that we said? The first thing we said was assume nu does not take the value negative infinity.
Yeah.
That's why we're playing with negative sets.
Mm-hmm.
Otherwise, just reverse the argument. So it doesn't take the value negative infinity, which will force this thing to converge.
Mm-hmm. Yeah. But does D have?
D has negative measure by assumption.
Yes.
The first thing we started with is if you have a set of
And it's
negative
not
measures,
negative infinity. Right.
and nu does not take the value negative infinity, and we're adding a bunch of positive things.
All right.
Okay, but that's about to contradict what we're doing here.
Yeah.
So we're about to find a contradiction with the existence of a set of positive measures.
Okay. Gotcha.
So if T of n is at least nu of S for all n, does everybody see how we got this? This is the soup over all the nu's. And so this is one such subset that survived all the cuts. So it's part of the thing that T of n is souping over. But, so that means nu of En, which is this minimum, it's at least minimum of 1 and nu of S over 2. Can you see both of these at the same time? Yes. Right? This is, by definition, at least 1 or Tn over 2, but Tn is at least nu of S. So we have this inequality, and that spells trouble for an infinite sum of things that don't depend on n, where this is positive, this is also positive. So that implies that the sum of nu of the ENs diverges, which implies nu of f is minus infinity, and that's a contradiction because we said nu doesn't take negative values. Negative infinity as a value. So one more time, all we did is we took this D, original D set, we found the most positive set, or not even the most positive set, but like a positive set, E0, to remove out of it. And it's not even that the set is positive, it's just the set that is the largest, a close to the largest positive value. And then we threw that out, and then we found more things that were positive, and we threw out more things that were positive. Maybe we threw out some negative bits too along the way. But what was left after all this discarding is like a totally negative set F. And if it's not totally negative, then it has some positive component, and that positive component will be at least the soup that we were measuring every time. And if that's the case, then this series diverges, and so we have some finite negative value minus a positive infinity. And this is why we don't want plus infinity minus infinity. So there's just some finite thing minus a positive infinity that makes nu of f have negative infinity as its value. And from the very beginning, the reason we're playing with negative sets is that we assume nu doesn't take the value negative infinity. Does that make sense?
Did we assume at the end? Yeah, we have nu of d is finite from the beginning.
Well, nu of d is finite because from the very beginning we assume nu of d is negative, and it doesn't take the value negative infinity. So
Yeah.
it's automatically finite. Okay, this argument we're going to run one more time, and it will prove the Hahn decomposition. Okay, so I think we can do it. What should is anyone still writing? We're okay. This makes sense? Not going too fast? All right. So let's I don't know what to do.
Why was it that some of the ENs diverges at the end, assuming that they're greater or equal to the minimum of...
Because now this doesn't depend on n. They're all at least some positive number.
Yeah, just it's constant for each
It's
n.
constant for each n.
Yeah.
That's the beauty of this argument.
Yeah.
Okay. All right, so let's prove Hahn by a very similar argument, and let me try to do it in 4 minutes. Proof of Hahn. So start with n0 be the empty set. Let Sn, so we're going to run induction. Let Sn be the infimum over, we're sort of doing the same thing but in reverse. The infimum over all the sets nu that are in X take away the nth negative set. So first we take away nothing. We look at the smallest value nu takes. Remember, nu doesn't take the value negative infinity. This still could be negative infinity.
Yeah.
Could be negative infinity. The nth could be without, but none of these are equal to negative infinity. So there exists a set Dn in X take away Nn, for which its new measure is at most now, well, what I want to say is Sn over 2, but that could be very negative, so let's take the less negative of this and negative 1. So we're just running the same argument from the other side. Okay? By the way, this number, because the empty set is here, this number is definitely a non-positive number. All right, so this is just the same argument. By the lemma, so this is less than 0, by the lemma about negative sets, by the lemma about sets of negative nu measure, by lemma, there exists a subset of Dn whose measure is even less than Dn, and Nn is negative.
Is this the same n plus 1?
This is how I'm getting from, I guess it's n plus 1. Yeah. Oh, I guess I called this Fn. Let's call this Fn. It was called F in the lemma, right? There exists an F, which is a subset of D, which is negative, and now you let n plus 1 be the previous negative values, disjoint union, because they were all being taken out of X take away, Xn, Fn. So one more time. We start by taking away nothing. N0 is the empty set. We look at the smallest, the infimum over all the values of nu. The infimum could be negative infinity even though the values never are. This is non-negative. There's some set which has nu, well, if this is negative infinity, then let's set it to negative 1. Otherwise, just think about Sn over 2. That's a negative set. By the lemma, that's a set of negative measure, but that doesn't mean every subset of it has negative measure. The lemma says there is a subset of it which is actually negative, and its value of nu only decreases, and we're going to add that on, chain that on, to get the next value of this set n. And so when we continue this induction, so at the end, let n be, I guess it's just this disjoint union of all of the fn's, which is the not disjoint union of the n's. All of the fn's are negative. Countable unions of negative sets are negative. This is negative. And the claim is that if I take away, so the claim is that x take away n, which I will define to be p, is positive. And the argument is the same as before. If not, there exists some set, let's just call it E, in P, which with nu of E strictly negative, and that has survived all of these removals of Fn. So all of the Sn's are less than nu of E. I'm just running the same exact argument with all the signs reduced, turned the other way around, which implies the nu of all of the Fn's is at most nu of E, or nu of E over 2, wherever it was, nu of E over 2, and I guess I need this or negative infinity. But anyway, nu of E definitely isn't negative infinity, so then we're done. Then we're done. Nu of n is equal to the sum of the nu of fn's, and if this is strictly negative, then this goes to minus infinity, and that is a contradiction.
Why is nu of fn less than the nu of E over 2?
For the same reason as before, the nu of fn is at most nu of dn, and dn was constructed to have nu at most Sn over 2. So all I'm saying is Sn is a upper bound for, I guess it could be, Sn includes E in the things that we were checking for in the supremum or infimum. Okay, so it's just the same argument run one more time with the role of positive and negative reversed, and using the lemma to get that this set n is a negative set. So P is indeed positive, and I guess I can leave it as an exercise, but to prove the uniqueness. But it's very, very easy. P symmetric difference P prime, if there's another, if P prime n prime is another decomposition, then what is P symmetric difference P prime? Well, it's let me, okay, I can either do it very quickly. Let me leave this as an exercise. It's P intersect n prime or P prime intersect n. But anything in here is both positive and negative, and hence null, and anything in here is positive and negative, and hence null. Okay, and this is also equal to n symmetric difference n prime. These are null. These are null. All right, that is the Hahn decomposition theorem. That is where we will